Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Beyond the event horizon, the mysteries of Hawking radiation. Hawking radiation, a groundbreaking concept proposed by the physicist Stephen Hawking in 1974, represents one of the most fascinating and paradoxical phenomena in theoretical physics. It bridges the realms of quantum mechanics and general relativity, two fundamental theories that typically operate in separate domains of the universe. Hawking's insight into black holes and the radiation they can emit fundamentally reshaped our understanding of these enigmatic cosmic objects, challenging the notion that nothing can escape their gravitational grasp. To comprehend Hawking radiation, it's essential to first understand the nature of black holes. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. This immense gravitational pull arises from a singularity at the center of the black hole, a point of infinite density where all the mass of the black hole is concentrated. Surrounding this singularity is the event horizon, a boundary that marks the point of no return. Anything crossing this boundary is irrevocably drawn into the black hole, seemingly lost forever. Traditionally, black holes were thought to be perfect absorbers, swallowing matter and energy without emitting anything. However, Hawking's revolutionary theory revealed a surprising exception to this rule. By combining principles from quantum mechanics with the curvature of spacetime described by general relativity, he showed that black holes are not entirely black. Instead, they emit a faint, nearly undetectable radiation, a phenomenon now known as Hawking radiation. This emission occurs due to the peculiar behavior of quantum fields near the event horizon, where the effects of quantum mechanics and gravity intersect. At the heart of this process are virtual particles, a concept arising from quantum field theory. In the quantum vacuum, which is far from being truly empty, pairs of particles and antiparticles constantly appear and annihilate each other. Near the event horizon of a black hole, the intense gravitational field can separate these particle pairs before they annihilate. One particle may escape into space, while the other falls into the black hole. The particle that escapes becomes what we observe as Hawking radiation, while the one that is absorbed effectively reduces the black hole's mass. This process defies the conventional wisdom that black holes only grow larger as they consume matter. Instead, Hawking radiation implies that black holes gradually lose mass over time, a phenomenon known as black hole evaporation. The rate of this evaporation depends on the size of the black hole. Smaller black holes radiate more intensely than larger ones. If a black hole emits more Hawking radiation than it absorbs from its surroundings, it will eventually shrink and vanish entirely, leaving behind a profound theoretical question about what happens to the information it once contained. Hawking's theory is not without its challenges. For one, Hawking radiation is incredibly weak, making it nearly impossible to detect with current technology. The temperature of the radiation is inversely proportional to the mass of the black hole, meaning that for stellar mass or larger black holes, the radiation is far colder than the cosmic microwave background radiation that pervades the universe. As a result, any Hawking radiation emitted is effectively drowned out by this cosmic noise. Only extremely small black holes, if they exist, would emit Hawking radiation at an observable level, but no such objects have been conclusively identified. Despite its elusiveness, Hawking radiation holds profound implications for our understanding of physics. It challenges the idea that black holes are eternal and raises deep questions about the nature of information and its fate in the universe. If a black hole can completely evaporate, what happens to the information about the matter and energy it consumed? This conundrum, known as the black hole information paradox, strikes at the heart of quantum mechanics and has driven decades of debate and research among physicists. Building on the profound implications of Hawking radiation, the second layer of understanding delves deeper into the mechanics and consequences of this phenomenon, challenging our grasp of the universe's most fundamental principles. To appreciate the depth of Hawking's discovery, we must explore its connection to the strange and fascinating interplay between quantum mechanics, thermodynamics, and spacetime itself. One of the key aspects of Hawking radiation lies in its unexpected link to thermodynamics. Before Hawking's work, black holes were thought to be purely absorbing entities, with no temperature or entropy. However, the concept of Hawking radiation introduced the idea that black holes have a temperature directly proportional to their surface gravity and inversely proportional to their mass. This temperature is incredibly low for most black holes, making it practically undetectable, but its theoretical existence was groundbreaking. The introduction of temperature implied that black holes must also obey the laws of thermodynamics. The first law of black hole thermodynamics relates changes in a black hole's mass, surface area, and angular momentum to the energy it absorbs or emits. Meanwhile, the second law, stating that the entropy of the universe must always increase, found an intriguing parallel in the surface area of a black hole's event horizon. Stephen Hawking and Jacob Bekenstein demonstrated that this surface area corresponds to the black hole's entropy, providing a new perspective on how black holes interact with the rest of the universe. These thermodynamic connections led to one of the most significant philosophical and scientific puzzles, the black hole information paradox. According to the principles of quantum mechanics, information about physical states cannot be destroyed. Yet, if a black hole evaporates completely due to Hawking radiation, it seems that all the information about the matter and energy it consumed would vanish with it. This apparent violation of quantum mechanics poses a fundamental challenge, forcing physicists to question whether we fully understand the laws governing the universe. One proposed solution to this paradox suggests that information is encoded in the Hawking radiation itself, but this idea presents difficulties. Hawking radiation is random and thermal, lacking the complexity required to encode detailed information. Another hypothesis involves the concept of black hole complementarity, which suggests that information is both reflected at the event horizon and simultaneously stored within the black hole, resolving the paradox without direct contradictions. More speculative ideas involve the possibility of firewalls at the event horizon or the idea that black holes might lead to alternate universes, where the information could reside. Hawking radiation also raises questions about the ultimate fate of black holes and their role in the cosmos. Over unimaginably long timescales, black holes that are not actively feeding on surrounding matter will emit more Hawking radiation than they absorb, gradually losing mass and shrinking. Smaller black holes emit radiation more intensely, so as they shrink, the process accelerates. In the final stages of evaporation, the black hole would reach an incredibly hot and energetic state before disappearing completely. However, the details of this endgame remain speculative, as current physics cannot fully describe the conditions of a black hole's final moments. This gradual evaporation process could have profound implications for the future of the universe. In a far distant epoch, long after stars have burned out and galaxies have dispersed, black hole evaporation might be one of the few remaining energetic processes in an otherwise cold and lifeless universe. The remnants of these evaporated black holes might carry answers to some of the deepest mysteries of physics, from the reconciliation of general relativity and quantum mechanics to the ultimate fate of matter and information. Beyond its implications for black holes themselves, Hawking radiation provides a tantalizing glimpse into the possibility of a unified theory of physics. The process involves quantum fluctuations, space-time curvature, and thermodynamic principles, making it a rare instance where these disparate areas of physics converge. Physicists hope that understanding Hawking radiation more deeply could illuminate pathways toward quantum gravity, a theoretical framework that would unify general relativity, which governs large-scale phenomena, with quantum mechanics, which rules the microscopic world. Hawking's insights have also inspired physicists to reimagine the very nature of black holes. Instead of viewing them solely as regions of no escape, they are now seen as dynamic entities with life cycles, capable of influencing their surroundings in unexpected ways. This shift has implications not only for the study of black holes but also for the broader understanding of the universe's evolution, the behavior of extreme spacetime conditions, and the fundamental laws that govern existence. The exploration of Hawking radiation extends beyond the black holes themselves, offering profound insights into the nature of the universe and the limits of human understanding. In this final discussion, we consider the broader implications of this phenomenon, its connections to emerging theories, and the ongoing questions it poses to physicists striving to unite the laws of nature. One of the most profound implications of Hawking radiation lies in its potential to reconcile the apparent divide between general relativity and quantum mechanics. These two pillars of modern physics describe vastly different aspects of the universe. General relativity excels in explaining large-scale phenomena like planetary motion, black holes, and the expansion of the universe. On the other hand, quantum mechanics governs the subatomic world, dictating the behavior of particles and the fundamental forces. Hawking radiation, arising from the interplay between these realms, serves as a rare bridge, highlighting the need for a unified theory. This unification effort, often referred to as the quest for quantum gravity, seeks to understand how spacetime behaves at the smallest scales. Hawking radiation offers clues by demonstrating how quantum fluctuations, tiny disturbances in the vacuum of space, interact with the intense gravitational fields near a black hole's event horizon. While a complete theory of quantum gravity remains elusive, frameworks such as string theory and loop quantum gravity attempt to describe this intersection. These theories suggest that spacetime itself may be quantized, consisting of discrete units rather than a continuous fabric. As theoretical work continues, Hawking radiation also prompts questions about the very fabric of reality. If black holes can lose mass and eventually evaporate entirely, the nature of their contents and the role of spacetime in preserving information must be re-examined. One speculative idea involves holography, the concept that all information about a black hole's interior might be encoded on its event horizon, much like a 2D surface can contain all the information needed to describe a 3D object. This holographic principle has broader implications, suggesting that the universe itself might function in a similar way. Hawking radiation also challenges our understanding of cosmology, particularly the role of black holes in the evolution of the universe. Black holes are not just destructive entities, they are also engines of cosmic transformation. As they emit radiation, they interact with their surroundings, potentially affecting the distribution of matter and energy on a grand scale. In the distant future, as black holes evaporate completely, the universe might enter a new phase, where the remnants of these objects, possibly in the form of faint, lingering energy, continue to influence its structure. In addition to these theoretical implications, Hawking radiation inspires new avenues of experimental research. Although direct detection remains beyond current technological capabilities, scientists are developing innovative methods to study analogous phenomena. For example, laboratory experiments with ultracold atoms or simulations of spacetime using light and sound waves have produced effects similar to Hawking radiation, providing valuable insights into its underlying mechanics. These experiments, though not direct observations, bring us closer to validating the theoretical predictions made by Stephen Hawking nearly half a century ago. Finally, Hawking radiation touches on profound philosophical and existential questions. It compels us to confront the limits of human knowledge and the mysteries that remain beyond our grasp. What does it mean for information to be lost or preserved? How does the universe balance the competing forces of creation and destruction? And, perhaps most intriguingly, how does Hawking radiation fit into the broader narrative of the cosmos, from its explosive birth in the Big Bang to its potential end in a cold, dark future? The legacy of Hawking radiation extends far beyond the boundaries of black hole physics. While many questions remain unanswered, the study of Hawking radiation continues to illuminate the path forward, offering a glimpse into a reality that is both astonishingly complex and profoundly interconnected. Stephen Hawking's revolutionary insight not only reshaped our understanding of black holes but also opened the door to new realms of exploration, ensuring that his contributions will resonate for generations to come.